So moving on to Rob Lamb's second presentation that I'm covering for, and this is focusing very much on money, although it says energy efficiency, that's really what it's all about. So it looks at ways of reducing energy consumption in refrigeration systems through a number of approaches. Reducing the heat load is the most obvious one, in fact. If we can do less cooling, then that has to be a good thing from the energy and from the spend point of view. And it's amazing the amount of refrigeration systems that are running, but they're not actually contributing anything beneficial to the flow process, whether that's cold storage or whiskey bottling or cheese production or whatever. The system is running, but it really ought not be running. And as a contractor, I shouldn't be saying to you, make your refrigeration system smaller, but it's definitely the best way to save energy is by right-sizing the system. Component selection is the second thing. When you're looking at the choice of components, have you gone to a contractor that says, you have to use this compressor because it's the one that we offer? Or do you go to a contractor who says, I've looked at 5 different types of compressor, in my opinion, for your application, number 3 is the best bet. So equipment choice has a big part to play in energy efficiency. Looking at the temperature levels the system is operating at and being a little bit smart about the way you do it is another way of reducing energy. And then finally, measurement and analysis of the system to make sure, this is one of my real bugbears, my pet hates, make sure that it's still operating next year and the year after and 10 years after as well as it was operating when it was new. And it's incredible the number of systems that never get checked. They get put in brand new and they're operating, but nobody ever goes back to see is it still running in the way that it's supposed to be running. So there's a lot of benefit that can be gained just by having the ability to do that exercise. So some numbers, a bit of audience participation, relevant to the presentation. If I say 80%, what do you think I would be talking about? Any takers, 80%? 80%? Okay, Stuart, you look like you've got an answer there. Come on, you know you want to. You know you want to, go on. No? 80% is roughly the amount of the energy that is used in the compressor of the refrigeration. We talk about the compressor as being the heart of the system. In a cold store, it might even be higher. It might be as high as 90%. In a chill store or a water chiller, probably more like 80%. Another number for you, 10%. It's obviously not the rest of the energy, because if that's the level of your arithmetic, you've definitely got problems. But what would 10% be? Willie's heard this presentation before. You've got to know what 10% is. No? Any more? It's actually typically the amount that we reckon we could save by going to a typical system that hasn't been particularly well looked after and doing an analysis. It's relatively easy to make a 10% reduction in the energy. And then less than 1 year, maybe a little bit more obvious, if there's that kind of a saving to be made, this is typically the payback that you can be taking to your boss and say, if we do these few small things to the plant, we can save energy and it will have paid itself back within a year. So it really ought to be a no-brainer, but people don't do it. It's really quite incredible. So the first one, eliminating cooling load. Well, there's a whole bunch of ways. I mean, maintenance comes into it. Willie will be talking about maintenance later, so I don't want to steal his thunder particularly. But if you're running a cold storage operation, ingress of air is a major source of additional loads on the refrigeration system. So you can see 2 photographs here. In this one, a truck is backed up to the cold store door, and you can see there's a gaping hole above because they've backed a small truck up to a big door and they've not made use of the baffles or curtains to block it out. Now that looks okay. You think, well, there's probably not much of a draft coming in there, but in addition to the air coming in from outside, the air coming in from outside is carrying moisture with it. The moisture is invisible, so nobody really pays any attention to it, but it's actually at least 50% of the additional load in the plant. In this case, on this side, the door was broken. They didn't want it to close fully because they couldn't get it open again, so they, instead of repairing the door, they stuck a pallet underneath, leaving a gap along the bottom. And here, because it's warm, moist air coming into a cold area, you can actually see the effect of that moisture coming in. It's condensing on the floor and it's making the floor wet and slippy. So it's not only an energy hazard, it's a health and safety hazard as well. And if this was into a low temperature store, then that would be ice and it would be even more of a hazard. So These are things that we see day and daily when we go to cold storage sites, and they are absolutely appalling from a money point of view. This is money that's flowing out of the building because of the extra load that's coming in. To do some sums on that, if the air outside was at 32 degrees and 60%, and okay, we're in Glasgow, you might think, well, that seems kind of unrealistic, but we'll take that as the design condition, start with the worst case and work our way back. And the chamber inside is at, say, 2 degrees C, then the heat load on the plant for every 1 cubic metre per second of air coming into the building is about 100 kilowatts of cooling. With a plant COP of 3, that means about 33 kilowatts of electricity, 33 bar fires, if you want to think of it that way, just because there was a gap and there was air coming in. And you might think, well, 1 cubic metre per second, that seems like quite a lot. But actually, with a 1 square metre gap, a 1 metre per second draft is almost not noticeable. You know, that would be fairly typical. So if you've got a gap of a square metre, it's costing you 33 kilowatts in terms of additional electricity consumption. And if it was like that all year round, and okay, it was the summertime design condition, that at 10p per kilowatt hour would cost £10,000 a year. So you can see very quickly that reducing the air ingress is a great way to save money, reduce the load on your refrigeration plant. Another one would be to look at the infrastructure within the building, for example, using LED lighting. So in this case study where we made a change, we had 7 250 watt lights swapped to 7 48 watt LED lights, saved 80% of the electrical consumption, was about £1,000–1,200 a year. With intelligent control, you know, people sensors and so on, you could reduce that even further. And it actually gave better light quality as well. So they uprated the lighting system to a better system and saved money at the same time. The other example is booster fans within cold stores. It's quite common to see, in addition to the evaporators, there are extra fans around the room to spread the air around. But what we found is that these might be required under peak load conditions, but they don't actually need to be there operating all the time. Just by switching off the booster fans in a store, we saw no change in the temperature levels, but saved about £10,000 a year, again 10 pence per kilowatt hour. No effect on temperature control, and in this case, zero capital investment. It was just literally turning the switch off on the time when they're not needed. And you have the benefit that you can switch them back on if anybody feels that there's a need for them. So these little kind of things of going around and being quite critical about, do I really need to use that kilowatt hour? Can I switch it off? If it's a consumer of power and it's inside a cold space, then you're saving twice, because you save the energy used in the equipment, and you also save the energy used in the refrigeration system for dealing with the equipment. So I mentioned earlier the compressor is the heart of the system. Once we've reduced the heat load as much as we can, we need to look at the rest of the cycle to figure out what else we can do. And as I mentioned, the compressor is typically using 80 to 90% of the energy consumed in the system. The other major users, as was mentioned, are the condenser fans and pumps and the evaporator fans, and they would account for between 10 and 20% of the total. And there might be other loads like glycol pumps and so on, but typically they'd be smaller. So we'll focus on the core of the refrigeration plant, and the things that will help move your energy consumption in the right direction. So the compressor, 90% maximum use. Condenser and evaporator, 5 to 10% of the energy use. So most types of industrial compressors would either be a screw compressor or a reciprocating compressor. A screw compressor works best when it's on 100% load. If you use the slide valve to offload the compressor, then you impair the efficiency of the compressor. So it might perform well on full load, but it becomes quite inefficient on part load. If you use a speed controller, you can have the opposite effect, and you make the compressor more efficient when it's on part load. So if you've got an installation that runs most of the time on part load with occasional peaks at full load, it would make sense to add a variable speed drive and run the compressor backed off. With reciprocating compressors, a little bit different. If you're on part load, the efficiency of the compressor can actually improve because you're using the full heat exchanger surface on the condenser and the evaporator, but only doing part of the cooling process. So this would be a typical screw compressor type curve of, on the side here, it's coefficient of performance, which is essentially how efficient is the plant. You see good efficiency where we're at 100%, but it's tailing off as we drop off in capacity. If we were to use an economized compressor, then it's kind of better initially, but tails off again. What that means is if we're using a VSD, we can make the plant more efficient, better COP, down to about 50% load, and then it starts to fall off as we go below 50%. Whereas with a slide valve, we're dropping from day one. Fans and pumps behave differently to compressors, so you need to treat them differently in terms of energy saving. A lot of them are just either running or they're not running. And if you've got a condenser with 10 fans and you can manage to switch off half of them, that's great. You'll save half the energy consumption of the fans. So that's not a bad place to be. However, if you control the speed of the fans, you've got a much stronger lever for improving the efficiency. So a fan which is running on full speed will consume 100% power. That's kind of our benchmark. If we manage to back off the speeds by using a variable speed fan, and there are lots of them available in the market now, you don't need to buy a separate drive. You can actually have the variable speed built into the fan. If we drop to 75%, speed on the fan will still deliver 75% of the airflow, but we only consume about 41% of the power. And if we take it even further and reduce the speed down to 50%, we'll only be consuming 12% of the power. The same goes for variable speed on pumps. The problem with pumps is that as you drop the speed, you reduce the capability to overcome pressure drop. So you need to be careful. If you drop the speed too far in a pump, then it'll be deadheaded and there'll be zero flow. The same kind of applies to fans, but there's generally much less of a resistance to flow. If there's an air duct on the downside, you need to be a bit more careful with variable speed on the fans. But there's huge opportunity for saving energy by reducing speed on fans. If we look at what happens when you reduce the speed of the fan, you're actually making the condenser less effective, so you'll raise the pressure that the compressor runs at. So there's a trade-off to be had. You don't want to turn the fan off completely and have the compressor running much harder than it would have to. But if we take a sort of graph, just a cartoon of ambient temperature as time goes by, and we look at what would happen with fixed speed fan control, switching fans on and off, you get some fairly big steps of fan capacity. On the compressor, what you would see at the same point is a sort of spiky compressor performance where it's actually running fairly inefficiently a lot of the time because the condenser is running less fan and higher head pressure. If we use variable speed to match the two, then you see we can track the change in ambient temperature much more closely. So the effect of the fan needs to be balanced against the effect on the compressor, and this is something that in Star Plant we do this automatically within the control, but we can actually supply a product that can be retrofitted to other plant, which is called an Aether controller, which is a bolt-on to the condenser, and it will actually optimize the condenser fan speed based upon what the compressor is doing. It looks at the two sides and balances the seesaw. As I say, it's built into our own plant because we write our own software, but it can also be retrofitted to other systems. Another case study to show you is the effect of changing the temperature in a warehouse. Retailers have asked us over the years to look at their energy consumption and come up with ways that we can improve things. In one case, we were able to increase the storage operating temperature by 2 degrees C without having an adverse effect on the product, and delivered a significant saving to the end user in energy terms. And I'll just very briefly talk through the background to that. So raising the compressor operating temperature, the cold end of the compressor, by 1 degree C will save between 2 and 3% of the energy that the compressor is consuming. In this case, we raised the store temperature from 2 degrees to 5 degrees. It was checked with the trading law people within the supermarket company, and they said, yes, we're still happy with that. It was operating at the lower temperature because they wanted to have a bit more leeway in the event that there was a problem. But they looked back at the operating history of the plant and they said, well, we've never had that situation, so we're penalising ourselves to give ourselves a safety belt that we don't actually need. So they were happy to raise the store temperature provided the plant could maintain its reliability levels. We then did that by just putting an offset on the existing controls and maintained the temperature at the product level at the same level as it had been before, but by running the plant more efficiently by raising the suction temperature by 2 degrees. Half of the benefit that was received, we did this across 5 of their warehouses, and half of the benefit in each case was achieved through offsetting the temperature, and the other half, and that was effectively by measuring the temperature at ground level instead of ceiling level, and the other half was achieved by raising the temperature. So there was up to 20% saving in energy within this distribution centre by just making these simple changes, moving a sensor which didn't cost a great deal and changing a set point which cost even less. And on average, the saving of the offset was on average 7% across the 5 DCs. So that kind of is in line with the 3 to 4% kind of 3% figure per degree C. If you're running at -20 and you can run at -18, you could expect to save about 5% of your energy consumption. And that's why we say 10% is not an unrealistic number to achieve. So key aspect of energy saving, and we're just moving to the conclusions now, is understanding the current situation, making changes, and then being able to make a comparison. How was it before and how is it after? On the STS booth at the back, you'll see a demonstration of a system that we call Ethos, which is a fairly new development, a method of measuring and then assessing operation of refrigeration systems. And it's designed to improve energy, but actually we found lots of other clever ways to use it. It's really interesting. In one case, a user was saying, I think I need to buy a second chiller because we're going to extend our production process and we don't have enough cooling capacity. And by installing an Ethos system, taking readings and looking at the way that they used their plant, we were able to say to them, actually you don't need a new chiller, you just need to reconfigure the existing system that you've got. So that not only saved them the energy cost of running a second chiller, which would have been substantial, it saved them the capital cost of buying the chiller and getting it installed, all for the sake of doing some measurement. So it really is a very, very powerful tool. What it's doing is taking readings of operating pressures, temperatures, ambient temperature, product throughput, whatever you want to measure can be fed in. The data is sent off-site and is then analysed with various algorithms that STAR have developed to look at the optimal performance, and then it turns that back into money and says, if you were able to do this, it looks like your plant's not operating ideally. If you're able to do this, then it will save you this much money, and making that change might cost you so much. So it might cost you £1,000 to make the change, but it'll save you £2,000 a year. That's the way that Ethos presents the information back. So it makes it very easy for the maintenance supervisor or the engineering manager to go to the MD or the finance director and say, look boss, we really need to be doing this because we'll save money. And then after they've done it, they can take the report back and say, okay, we made that change 6 months ago. Here's what it looked like before and here's what it looks like now. This is really, really powerful because the biggest challenge that engineers have is getting money out of the finance people, let's face it. So anything that can make that easier has to be a good thing. And as I say, the presentation is all done in a manner which is trying to make it non-technical, make it more financial so that it's more easily understood. The alternative would be effectively operating blind or relying on the guy that you pay to do maintenance visits to tell you that he doesn't need to come and do maintenance visits. And again, as a contractor, I shouldn't really be telling you this, but you know that would be the likely scenario. Fred's always come in and done our maintenance. He's a good guy. He'll even turn out on a Sunday morning if he has to. So we trust him. But his vested interest is not necessarily in making the plant more efficient. So this is a kind of conscience for the contractor, if you like. It's there on his shoulder saying, well, what if you try this, what if you try that? It'll give a benefit. So there's all the things that it can do, monitoring the cooling requirement, benchmarking against what we think good practice would look like, giving real-time data measurement and comparing it with what was happening previously, and then looking for shortfalls in performance and finding ways to correct them. One example was we were measuring a plant that had 2 belt drive fans on the plant, and one of them was performing way better than the other. So we went and investigated and found that the belt was slipping on one of them. So just for the sake of tightening up the belt, we were able to improve the plant performance on the one plant. We kind of dropped the ball a little bit at that point, because what we didn't notice was that the other plant now wasn't performing quite as well as the one that had been improved, and actually the belt was slipping slightly on the other one as well, so we could have done even better on the one visit. So we had to go back and make a second adjustment once we looked at the figures again. But it's that kind of powerful tool that's saying something and this is not quite right, go and take a look, because you can save yourself some money, and as I said, it all comes back to money. So, just to summarise the things we've talked about, minimise the amount of heat load that you're applying to the plant. Better door control is one example. Reduced electrical loads within the space is another. Improve the refrigeration plant performance itself. Once you've minimised the amount of work it has to do, make it as efficient as you can. Look at the compressor control, look at the fan control on the condensers and on the evaporators and in the space, and look at the probe location within the room, and is it really in the best place, or is it making the plant run too much? And then continuously monitor and assess and compare with what it was doing yesterday, last week, last month, last year, and continually seek ways that you can bring that number down. And it's amazing the things that can be found once you really start digging.